we've got two very excellent speakers for you this afternoon. Starting off with Cheryl, who's going to lost your time. Go classical groups with generated small classical subgroups.
Thank you, Derek, and I'm absolutely delighted to be here. I mean, I remember, was it 5 years ago, we talked, Culver and I went to talk with the director of the Newton Institute about the possibility of having a group theory semester, and so now it's really happening, so fantastic, and thank you for the opportunity to speak in this workshop. I'm going to talk about some work, a huge project for me that's been going on for quite a number of years and will probably continue for a few more years yet. So we're kind of in the middle of it. So the situation, or the input, I guess, is that we've got a finite classical group, usually given by some small set of generators, but I won't be really talking so much about the implementation details. So it will be a n by n classical group, maybe unitary, symplectic, orthogonal, that sort of thing, over a field of order Q, or SL. But my problems have always been with the non-linear issue here. And the problem is to find a classical subgroup of G. So this H is going to be a classical group on a relatively small, smaller subspace. So really I'm looking at finding an orthogonal decomposition of the natural module V, and the H is going to be the classical group on W, I guess, cross the identity. So it's going to fix W per pointwise, and it's going to be the classical group on W. That's what I'm trying to find, okay? So thank you, Heiko, for the fantastic survey of the methods of constructive recognition of classical groups. This is really looking at one of the major components of the classical reconstruction or construction of standard generators. One of the focuses there is to, I guess, descend and find a small two-dimensional SL2, say. And so if we're going to find a fairly small dimensional non-degenerate subspace in a classical group there, we're going to recurse down and find an SL2. So that's this particular component where we're going to be looking at. So it's very much in line with the methods, the algorithm of Heiko and Charles and Eamon and Frank that's been published. But we're very much interested in the complexity of this particular part of the method, and we're also very much interested in perhaps taking a slightly different track towards the eventual algorithm. So the work I'll be talking about currently is current collaborative work with Alice Niemeyer and Stephen Glasby, and some of it with Frank Lubeck. In the future, I hope it will be a collaboration also with Alice and Max Horn to produce an implementation of this full gap. And in the past, some of the components of it that I will be sketching and talking about has been collaborative work very much on the ideas of Akos Seress, and some also with Shukru Yeltsin-Kaya. Okay, so how do you find H and how do you find W? So the idea is that Heiko and everyone, I'm going to have to say Heiko et al., aren't I? Heiko, Charles, Eamon, and Frank use, and it's very similar to what Akos was also wanting to do, how to find H. Well, they all say Well, you find two elements, G, G prime. What do you want these elements to be like? What do you want them to do? Well, there's going to be a G invariant orthogonal decomposition, V as U direct sum F. And this F is actually U perp, but I'm calling it F because I want G restricted to U to be an irreducible PPD element. I'll say what that is in a minute. And I want F to be the fixed point space of G. And I want U to be non-degenerate in the classical set case. Okay, so first, what do I mean by a PPD? So if the dimension of U is M and the fields of order Q, and of course I'm finessing here a little bit. If it's the unitary case, maybe we think of the field as being Q squared, but I'm talking about all the cases. It's just going to be Q at the moment. To be a PPD element, I want there to be existing a prime R dividing the order of G, and R should divide Q to the M minus 1, and R should not divide Q to the I minus 1 for I less than M. This is kind of an over-the-top sufficient condition for an element to be irreducible if it has such a prime divisor in its order, right? So these PPD elements will definitely be irreducible on U. Okay, that's fine. So I want the whole setup to also apply to G prime. So for G prime, we'll have its U prime orthogonal F prime, and G prime will be a PPD element on U prime, and M prime will be that dimension. Okay, so Heiko and everyone use these sorts of elements, so they want to find these elements, and the group H is going to be generated by the two elements, G and G prime. So what's W? Well, it's going to act on the sum of U plus U prime, and it's going to fix the intersection of F and F prime. And what we're going to want is that U intersect U prime is going to be 0. So W is going to be the direct sum. We're going to want this to be non-degenerate. And we're going to want H to essentially be the classical group on W. So this is essentially how the Heiko et al. Algorithm proceeds to what they call find the first group. So it's the part of the algorithm where we're finding the first group. And the first group is this classical group here. Now, they would have looked at finding these dimensions, M and M prime, somewhere between 1/6 and 1/3 of N, so that the W is going to have dimensions somewhere between 1/3 and 2/3 of N, And so in one step, we'll go from dimension n to something around a half, and then you just do this log n times, and you get down to your two-dimensional space. Well, my entrance into this problem was Akos asking me, and then therefore me and Alice, to do all of this with m and m prime being roughly log n. So he asked us to do this. We thought this was just incredible. How are we going to do it? So how are you going to find these elements g and g prime? So the way we're going to find them is kind of the way is done in the other paper, right? So how do we find g and g prime? Well, let's look at one of them. It's the same for the other. How do we find g? We're going to make a random selection in the classical group G, and we're going to hope that there is that there is an X invariant non-degenerate subspace U of V of the right dimension So in fact, we're going to ask for m to be between log n and 2 log n. Okay, so it's non-degenerate. We're going to want x restricted to u to be an irreducible PPD element. Let's say relative to one of these PPD primes R. And then we're going to raise x to the power its order divided by r, and that's going to be the element g. So what would we know about g at this point? So it would have order r. If we're thinking of how x acts on u, well, it might or might not. We're going to hope that it's got, we're hoping, we would like it to still be acting as a PPD element. You know, we might have been really unlucky, so you have to be a little bit careful here, right? We might have had r squared dividing the order. Something horrible might have happened. And we would like it to fix the complement of this non-degenerate space, U. So how could we guarantee that? So some things bad could happen. Also, there could have been, it could be acting on several subspaces with the same dimension, so that it might not look exactly like we want it to look. So how are we going to guarantee that this is going to be one of our good elements? So let's think of the characteristic polynomial of x on V, and let's take f to be the characteristic polynomial of x restricted to u. Then, of course, f is going to be an irreducible polynomial, and it's going to divide the characteristic polynomial. And so the idea was to make sure that this was the sort of element that we wanted. We're going to ask that all other irreducible factors of the characteristic polynomial have degree coprime to n. It's a pretty draconian condition, but it's going to be good enough. So if all of the other irreducible factors have degree coprime to m, then on all of the other components, primary components of x acting on the space V, you're not going to see any R in the action at all. So when you do this powering up to get your element of order R, you will find that this element will fix the rest of the space, and it will really be acting as a PPD irreducible element on U. But the thing is, how easy is it to find such elements? So that was the first challenge that Akos said. He'd done all this experimental work, and he thought that you should be able to find them pretty easily. And this is what he wanted. He wanted us to show that there was sufficiently many of the elements in a classical group that you could get all of this sufficiently often with the m between log n and 2 log n. Okay? So that's the first thing that we did. So this is a paper which unfortunately didn't get published until after Akos's death, but he certainly knew all the results in it. It seemed to get lost somehow. This is Alice and me. And so we're picking our m between log n and 2 log n. And then we show that there exist constants C and C prime such that the probability that, let's say x is good, it means that x actually has all this stuff. It has this, I guess, unique, non-degenerate m-dimensional, that m-dimensional subspace, PPD element on it. Its characteristic polynomial looks like this, so that when you raise it up to the right power, you get the element that you want. That this probability is between C over log n and C prime over log n. So you'll need about constant number of log n of random selections to find one of these elements. I was kind of hoping that you could then say, what's for a particular n, and there's lots of values of n here, and you could just add them up. But I think that's not going to work, because these sets might or might not be disjoint. So if they were disjoint, you could add them up and say, okay, we've got log m choices of m's, and each one's given us a constant over log n. So we've got constant proportion, but that's probably not something we can prove. But they're fairly readily found. So what do these elements look like? Well, if we were to block a matrix, so the G that we're finding this way, so that we get this PPD element up here and the fixed point space there, well, Elise tends to think of them as like a little thing fluing around like this, and she calls them stingray elements. And I don't have much control over what Elise calls things. So, so these are stingray elements. And so what we want to find are two independent random stingray elements. So each will come along with its non-degenerate subspace U and U prime, its dimension M and M prime, and then we want to take the group generated by these two random stingray elements, and we want to hopefully find our small classical group. Okay, so yes, so we've done this little bit of it. We can find the elements. But there are a whole bunch of other things down here that we would like to achieve. And so we would like the u and the u prime to be disjoint. We would like their sum to be non-degenerate in the classical case. We would like g and g prime to generate a classical group. So the next thing that Akos did was, I guess he must have thought that he was running out of time or something. He just didn't care about this stuff. He sort of jumped over to this classical problem and saying, well, he would just assume that you would have your element g and g prime. So now we've got our stingray random elements g and g prime. We've got our non-degenerate subspaces u and u prime. We've got our numbers m and m prime. And so we've got this w, which is going to be non-degenerate, we hope. And it's u plus u prime, and u intersect u prime is 0. And we want to look at what is the chance, what's the probability that g and g prime is essentially contains the socle of the classical group on this space W. Well, the problem that Akos posed for us to look at here was not taking independent stingray elements, but instead finding one of them and taking the second one as a random conjugate of the first, which means that the m equals m prime. This has got even dimensional. And so these elements, in those days, he or we called them good elements. We didn't know about stingrays. And he wanted to know what was the chance that these two random, a good element and its random conjugate would generate the classical group. And so this is what we proved was that there exists a positive constant such that this probability is bigger than that constant. Almost. So who's we, and then what does almost mean? So there's paper 2015, and the authors are Akos Seress, Shukru Yalcinkaya, and me, and unfortunately that's published in the Journal of Algebra issue in memory of Akos. And we proved this, for SL, for SU, for SP with Q odd, and for the orthogonal groups, all of them as long as Q is at least 3. None of our computations, our estimates, were quite strong enough to make things work for Q equals 2, so we don't have a result there. We've got this funny exclusion here of symplectic groups needing Q odd. What happens for SP Q even is that when I say classical, I think you and we were thinking classical of the same type as the group we started out with. Now the thing is, if you start out with G being a symplectic group with Q even, and you take one of these subgroups generated by two good elements, it's never going to give you the symplectic group on the smaller space because it's always going to be contained in an orthogonal group. And so what we proved was, instead of this being the symplectic group, we proved that the probability that our H subgroup contains the orthogonal group is greater than a constant greater than 0 in that case. So it's kind of as good as you can get and fine. And so this was the case where these are random conjugates of each other. Or rather, one is given and the other's taken as a random conjugate. So there is still ongoing work, which is looking at the case where the G and the G prime are independent stingray elements, wanting to prove something rather similar to this. And the people involved there are Frank, Alice, Stephen, and me. We totally held up for 2 or 3 years because couldn't solve this issue. So, and so if I couldn't prove that, it was really, really easy to get my W being non-degenerate. What was the point of trying to prove that I'm generating a classical group on this space that might not even be non-degenerate? So I was asking Frank if I could weaken the conditions and maybe just assume that we were acting on this space modulo its radical. And Frank would sometimes say yes and then eventually said no. So it's all got totally held up for years and years until last December. So Alice and I worked on this a lot, 15 months ago in Bonn at the program there. And we wanted to show that sufficiently often, well, that's easy enough, to sufficiently often they're disjoint, and then sufficiently often they generate a non-degenerate one. Let me show you an example, a salutary example, because every time I think I'm just being stupid, I realize that there's an issue. You could suppose that our space has, say, this is the smallest convincing example I could think of. So I'll take a 6-dimensional space and the EIFIs are hyperbolic pairs, and maybe it's symplectic, or maybe it's unitary, or maybe it's O plus or something. And I found my G with its non-degenerate U, which turns out to be E1F1. And I found a G prime and its U prime non-degenerate, which is generated by E1 plus E2, F1 plus F3. So that could happen, that's fine. You can see that U intersect U prime is trivial, so they're disjoint from each other. So they're going to generate a 4-dimensional space, and so the W that you get, just looking at it, is generated by E1, E2, F1, and F3. So genuinely 4 dimensions, but its radical is as bad as it can get. It's 2 dimensions. So you've got M equals M prime equals 2, and I mean, I used to think, well, you've got this space and it contains G and that's irreducible on U, and it contains G prime and it's irreducible on U prime, and the space is just U plus U prime, so what kind of thing could possibly go wrong? Surely it's irreducible. Anyway, yeah, so bad things might happen, and so what we have to do is prove that the good things happen sufficiently often. So what we wanted to prove was that sufficiently often, this guy here, this W, really is non-degenerate and it has the maximum dimension, M plus M prime. Okay, so I've been bobbling on here. I've got plenty of time still? Yes. Yep, great. So I will probably finish early, but that's okay. So I wanted to talk you through what we're trying to do to get this chance of W being non-degenerate. So let's set up the problem. So we've got a conjugacy class C of stingray elements, and G is one of the elements in that conjugacy class, and we've got another one, and G prime is in that conjugacy class. And so I'm just looking at particular conjugacy class of the ones which we've found, and we want to know what is the chance, of of their W being non-degenerate. So G has got a non-degenerate subspace U associated with it, and G prime has got a non-degenerate subspace U prime associated. This is U's got dimension M, U prime's got dimension M prime, okay? So what we would like to know is what is the number of pairs G, G prime in C and C prime such that their associated U and U prime are disjoint, that their sum is non-degenerate. And then I want to divide that by the size of C and the size of C prime. And I would like, so my object is to prove that this is greater than some positive constant, okay? I'm in a particular type of classical group, and n is the dimension. Okay, so what is the first step we do? Well, having seen the picture of the stingray element up there, we know that G preserves this decomposition of the space U plus U perp, and so the centralizer of G is contained in the stabilizer of U, and all I really care about is these conditions on the spaces U and U prime that are fixed, right? So how do I get from this proportion? Well, this number here is the number of non-degenerate M spaces, possibly of a particular type. It would have to be, say, it would have to be even dimensional minus type if my group is orthogonal, because I have an irreducible element acting on it. M would have to be odd if it was a unitary type. M would have to be even if it's a symplectic type, because I need irreducible elements acting. So I'm sort of pushing all that under the carpet, but I've got all of these extra conditions as well. But this is the number of I just decided for the talk, if I could just use a notation like this, the number of m-dimensional non-degenerate subspaces of my n space. I'll just use that. So that's that index. And so this index, of course, is the size of the conjugacy class. And this is something else. It's like the number of G's that give you that fixed U. Okay? So I can, the bottom line, I can factorize by the number of M spaces, and then for C prime, the number of M prime spaces. And if I had a particular M space and M prime space, I'm really interested in the number of pairs U, U prime. This is non-degenerate M prime, intersect trivially and generate non-degenerate. Now, once I would have a particular good set, any old G's and G primes in the set would do on the top line. So the number of pairs G, G prime that I get for these good U's is the same as the number of G, G primes that I would get for any old choice of the U and the U prime. So they cancel out. So that little bit of group theory says this proportion that I'm interested in is equal to this proportion to do with linear algebra. So the next thing I do is say, well, yeah, the group G is acting transitively by conjugation on the M spaces, non-degenerate M spaces, so I'm going to fix one and do a little bit more of this easy computation. So I'm going to fix my U, and I'll be looking for the number of U prime such that U intersect U prime is 0, U plus U prime is non-degenerate. And this time, I'm just dividing by the number of U prime. So all of that's fine. We could have done this 3 years ago. So we want to prove that this is bigger than a constant. And this is where we got totally stuck. And when you see the solution, you think, how could we be stuck for so many years? But anyway, so what do we do next? So we're really interested. This is our space. This is going to be W, right? So how do I find W? Every time I've got a U prime, I've got a W. I mean, every time I've got a good U prime, I've got a non-degenerate W. And every, oh gosh, yes. I think I will need a little more space. And every time I have a particular W, it's going to contain the same number of U primes. So I'm thinking that I should be able to write that expression as, I'll come back to this thing, the number of W's times the number of U primes contained in a good W with all of the same conditions. So what do we know about W? It's supposed to have dimension m plus m prime, and it's got to contain U. And it's actually going to be equal to U plus U prime, because that's the condition, but also it's going to be equal to U orthogonal direct sum of U perp intersect itself, and this thing here is going to be a non-degenerate M prime space. And so the number of W that we get here is it's the number of M prime subspaces of U perp. Oh, sorry, perp. Yeah. So the number of W's that we want, so how are we doing this? So U perp has got dimension n minus m, and we're choosing an M prime non-degenerate subspace out of it. So we choose our W, and then we want that. And here we've got this on the bottom line. So what? So I'll just move that over to here. Okay. Now, I would sort of like to transform the problem into something else which is a little more different or tight or something. So this is, here I've got U is a given M space, non-degenerate, and W is a given M plus M prime space, non-degenerate, and I'm wanting to choose my non-degenerate M prime space in W with certain conditions. So if I'm looking at a proportion, I really should be dividing by the number of non-degenerate M prime spaces in an M plus M prime space, right? Well, that number's not there, so let's put it up here. So now that quantity is a perfectly good proportion, okay? And this quantity is something that I cannot figure out. But a miracle happens, and if someone can tell me what this is measuring, that would be fantastic. But it turns out that this, if you look at the Q power in each of these things, they all cancel out. And so this is actually some kind of number between 0 and 1, which we estimate. So it's some, let's call it constant. I mean, it's not really a constant, it depends on Q, but it's bounded, yep? So this is the constant. And now this is this other problem. So now we're looking at a given space, non-degenerate, of the right dimension, m plus m prime, and we've got an m non-degenerate space in it, and we're wanting to get the number, or proportion, number of m prime non-degenerate subspaces, which, well, they either u and u prime span w, or they intersect trivially and the other condition is implied. This is the hard thing. So we've been working very hard, and we proved that this is bounded below by some certain explicit constants. So we can get this nice constant, and it's not nice, but we can get it. And so this is what Alice and Stephen and I have been doing for the last few months, is getting at that, that quantity. We'll also just estimate this, and therefore prove that a constant fraction of the stingray pairs are fine. They give you the right sort of non-degenerate subspaces, and then we just need to extend and reanalyze what Akos and Shukru and I had done in this more general setting, which has advantages. For example, the dimension of W might sometimes be allowed to be odd, say in the orthogonal case, instead of it having to always be even in the other cases. So we think we're almost there, and I'm so relieved. I thought this was going to really kill me. So, oh yes, and so of course, oh yes. So this is then leading through to some computational problems in trying to make this into an implementable algorithm on the one hand, but on the other hand, just for fun, you can sort of strengthen the fact that this quantity is bigger than a positive constant into saying that if you were simply to choose at random an M space U in V, and again a random M prime space U prime in V, and if V has got dimension M plus M prime, and if this is a if V is a non-degenerate space, you know, unitary, symplectic, whatever you like, then there's a constant fraction of these pairs U, U prime, which are, oh sorry, it's not that, it's bigger. Dimension bigger than that. The constant fraction of these pairs, which both intersect trivially and span a non-degenerate subspace. So it's kind of cool. Does anyone know that? Because we thought this is the sort of thing that people ought to know, but we couldn't find it anywhere, and we didn't know it. Do you know that? If you just take a 2-space and a 3-space, or I don't know, whatever it is, 2-space and a 4-space at random, the constant fraction of them are going to be both non-degenerate and span a non-degenerate subspace. Do people know that? Well, that's good. Anyway, perhaps I'll close now. Thank you.
Instead of looking for U prime, why don't you quotient out U and then look for a subspace that's non-degenerate?
Well, that's what I thought. But that's not allowed. That's a very naughty thing to tell anyone who's trying to compute it, because computing in the quotients is really difficult and carrying along a lot of garbage, especially when the computer says yes. And so we were having to try to get the actual proof that this was going to be true, and we wouldn't have to do that. Because I was saying, well, why can't I just factor out the radical? Because the next is non-degenerate, and then I could prove that quite often I would generate the classical group. Yeah, but no, not allowed.
Where did the bounds log n? Why did you choose the bounds log n and 2 log n at the beginning?
That was Akos's suggestion. if you make the range bigger, then the whole thing works just fine.
Yes.
But he really had this idea that he would like in one step to descend from a classical group in dimension n to a classical group in dimension log n.
Yes.
And so it would be super fast descent, if that's your aim.
Yes. Well, yes. Well, I would just observe that. You see, if you just halve it, because of the complexity of multiplication, the time you spend in the halving can be more or less neglected in any case. So there's no need for such a rush.
But I think that, I mean, you guys used it our results.
Yes. Oh, yes. But I think, but yes, it's, you see, I mean, but I think that if you just halve the dimension, to say that.
But why would you do that if you didn't have to?
Oh, well, it's better to do it. It's better to, well, because it's so difficult. I mean, the principle, well, I suppose, oh yes, well, it's just the proof that's difficult. Yeah, okay, fair enough. Yes,
I mean, my impression, the algorithm seems fairly simple. You just choose random elements.
Yeah.
Oh, yes.
But then the theory is sort of telling you what you should be looking for,
Yeah,
perhaps.
yeah.
Yes, I take your point.
Yeah.
It's the same algorithm. It's just essentially, it's just.
I think, I mean, you do something different. You construct the classical group on both U and its perp, whereas this is not doing, I mean, you must be looking for different elements.
Well, doing different things.
Yeah. That's right. This is only the going down. Yeah, so I mean, Akos did say various things like you're going to construct your SL2, say, with a huge fixed point space and then do sort of random conjugates of that. Yes, and is better. Yeah. Yeah, yes.
Yes.
Yeah.
Okay, so we'll thank Cheryl yet again, and we'll
be
resume
great.
for the very final time at 14:45, and just under 15 minutes.